Vectors are nice and easy, as long as you get all the little baby concepts of a vector down. It's basically the same thing as learning square root systems, complex systems, and they're still talking. You remember learning the rules of radicals? And
Does
the
this
rules.
have something to do with it?
No, just the idea. It's something new that you're learning, but the ideas behind it are, they have their own little laws that you have to follow. So just like if you were adding radicals, multiplying radicals, dividing radicals, or adding complex numbers, multiplying complex numbers, dividing complex numbers, vectors have their own way of doing things. And as long as you know all the little rules of how to do things, they're actually not too hard. Vectors.
What is that symbol?
Wow. So a vector is a direction and a magnitude. So the best thing vectors deal with that is very common is force or speed or
Yeah, I've heard of
any kind of distance or any kind of measurement you can have that points in a certain direction. Describe a lot of things. Over here I have a picture of a hurricane. I don't know which one it is, but it has vectors included in it, and those vectors are how fast the wind is blowing. And as they change color, they actually are, get faster or slower depending.
So this is like direction and speed, or
Direction and speed,
velocity.
direction and force, direction and velocity, direction and
Torque.
So it's just,
torque is part of a
It's
vector.
just direction and something else.
Direction and something else, some kind of measurement
Okay.
that would have a reason to go in a direction. So if you have a 400-pound weight, in vectored language, it would be, here's your 400-pound weight. Which way would the vector go?
Straight down.
Straight down, because gravity is trying to pull it down. So your 400-pound weight would look something like this, if you were holding it up in the air. So this would be 400 pounds. So when you draw this, it has an arrow at the end of it, but the arrow really only says what direction you're going into. The length of this line, it actually stops here. This is called its magnitude. So the length of that vector becomes known as its magnitude, its size. And that's really all there is to vectors. No, there's more to it. If I have a vector here, we usually designate it, V is one of the common ones. You put a little arrow above it. That's called vector V.
Say what?
If you draw a V with an arrow on top of it,
Why
it's
are you
red.
drawing the
vector.
dash out from the V?
That's how I draw my V's.
It's cursive V. It's a Greek V.
You can do this too if you want. That's fine.
Okay, because I'm like, what?
Just don't do a V like this. I've seen people do V's like this, and that looks too much like
A
U, and U is also one of the common vectors. Alright, if that is vector V, one little trick you can play with vector V is I can move it anywhere on this board. So if I want, I could put vector V here. The only thing I have to keep constant is
The magnitude.
the magnitude, the length of it, and also the angle of the horizontal, so the direction doesn't change also. So I want that thing to go something like that.
Well, you said off the horizontal, so we could go down too.
Well, they point in any direction, but what I'm trying to emphasize is the direction doesn't change. The direction doesn't change. So I can move them anywhere I want, as long as I don't change their direction or their size. Now, are there operations I can do to vectors? Well, of course. You can have a 5-pound brick and then put on top of it a 10-pound brick, and all of a sudden it becomes
15 pounds.
15 pounds going in one direction. So you can take two vectors and add them. We'll get to that in a second. If we have a magic land, we can take a brick and double its size, and therefore it becomes twice as big, or 3 times as big, or 4 times as big. So we can scale it. That's called scaling it. We can't divide vectors. That's where one of the operations kind of falls apart. So let's talk about scaling.
Could you subtract them?
Yep. Well, if you can add, generally you can subtract. In most systems. I spelled it wrong already. Scalar.
Spell it over again.
Multiplication. Now, one thing that gets very confusing, especially with vectors, is you have to be really clear what's a vector and what's a scalar. A scalar is just a number, like 5 or 7 or -3. It's just any kind of number. So if this is vector V, I'll just draw it over again. Here's V. What would 2V look like?
Twice the size
twice the size, and still pointing
in the same direction.
same direction. So 2v would be leave v alone and add on another v if you want.
More magnitude.
So this vector would be 2v, twice as long. 3v,
Another
Three
one.
times.
3 times as long. What about a half v?
Half. the
You
length of
can't
the
do that.
original
Why not?
You said you couldn't divide.
V. If you know what. If you
You
know
cannot
what.
divide vectors. You can't have vector v divided by vector u. It doesn't make any sense. Take it over there first. They moved my doctor's appointment. So what would half of v be?
Half the length of the
Half
original
of
V.
the original v. So half of v would be like from here to here. So I'll move that over here. Half of v would be half as big, but still going in the same direction. All right. Weirdly enough, what about negative v?
It's just going in the opposite direction.
It's going in the opposite direction.
Oh, okay.
So you kind of go down this path, the same length as v, and that would be negative v. So it would be a point here in that direction. So that would be negative v. Right. That's scalar multiplication. Woohoo.
That's it.
Yeah, that's it.
All right.
All it does is basically scales it, literally. It just kind of extends it or shrinks it or reverses it direction. That's all it can do. But
Can it
the,
rotate?
but the line that it's on cannot change.
That answered your question. It can't rotate.
Once you rotate it, it changes direction.
Yeah, it changes the vector.
When you multiply by a scalar, the direction, all those lines are going to be parallel. If you drew them as literal lines. All right, so the next thing up is what does it mean to add two vectors?
That you have.
For instance, if I have a vector here, going in that direction, let's call that v. And I have another vector here,
Oh, those are in a different direction.
going in this direction, w. And I say I want to take these two vectors and add them. Well, the first thing you have to do for addition is make their start points be exactly the same as one technique. There are others. So I'm going to reposition them so that v is here and w starts exactly where v starts. Now, one way of looking at this, I always think of it as like a tug-of-war type situation. You have this weight, a rock or something, and it's sitting right here. And you attach ropes to it, that becomes the vectors. And vector v rope is someone pulling it, but not as hard as vector w. They're pulling a little bit harder. So when they're both pulling it at the same time and they keep that angle between them constant, then this rock is going to move in a certain direction. What direction will it move in? Will it move along w's vector, or will it move along v's vector, or something else?
In between them.
In between them, right? So you would expect the sum of these two vectors to be someplace in here. And I'm not going to say exactly where it is, but it's someplace in there.
It would be closer towards the W then.
But it'll be closer towards the W. So the technique is this. You draw a parallelogram. So the green line on the bottom, it goes this direction for a certain length. And I'm just, that's horrible.
Oh,
Let me draw. Dotted line is horrible, so we'll do the solid line. And then on the tip of W, you draw V as a parallel line, and you get that. And where they cross is
That's
where
the
you want
angle.
to aim. I wish I had a different color, but I don't. So this vector, from here to here, this would be V plus W. V plus W. It's a little bit between V and W, but the parallelogram decides what direction it's going in.
Would you always draw a parallelogram?
You don't have to. There's different ways of doing it. Parallelograms, opposite sides are congruent, right? Well, if this is vector V, I could have also done it as laid W out, and at the end of W, start V, and then it becomes a triangle. So it depends on how you want to do it. So if I had these two vectors, here's V, here's W, and I want to add them together, I could do the parallelogram setup where I take the 2 points and lie them right on top of one another, or I could take one of the vectors and start it at the end of the other vector. So here's v, and if I attach w from here, then the sum of the 2 vectors would be from here to there. It's just a neat little trick. It's just the triangle portion of it. So this would become v, well, kind of, plus w. That leads into law of cosines, law of sines, all that fun stuff. Eventually, it does. All right, now the tricky one is not addition. Addition most people get with the parallelograms or the triangle, one of the two. So this is addition. Addition. The one that's tricky is subtraction. I'll show you the long way and then we'll try to create a shortcut. Okay, so here is vector v. Here is vector w. I'll try to draw it the same as over there. Ah, I messed up, that's right. And I want to subtract them. Now remember, order of subtraction matters because subtraction is not commutative. So if it's v minus w, you get one vector. If it's w minus v, you get a completely different vector. All right, so I'm going to start off doing the same thing. I'm going to start them at the same point. So here's v. Here's w. I'll start it right here. Going on that way. There's w. And I want to subtract them. So I want to do v minus w. V minus w is my goal. If I do the parallelogram, it becomes v plus w. So what I need is, what does it mean to be v minus w?
Is it another shape?
It's still going to be a parallelogram. I can force it that way.
You just go the other direction.
What do you mean the other direction? What goes the other direction?
The W.
The w. Because it's minus w, that becomes scalar multiplication, and negative takes your vector and makes it go
Other way.
the other way. So I can take w, and this would become
Negative w.
negative w. And then I can go v plus negative w would be the parallelogram. Get that blue marker here. So I would draw v down here someplace. And w would go this way, or negative w. And where they hit is where you want to aim for. So this vector here is v minus w. So one way of doing it is to flip your vector around and make it point in the other direction, and then just construct your parallelogram using positive v and negative w. So that becomes v minus w. Now, if you think about it, if I take this blue line and pick it up and drop it over on the right-hand side of the picture, it fits right between these two arrows. So v minus w is also here. So you don't really have to draw the parallelogram, you could do the triangle picture. But the trick is this. If it's v minus w, it starts on w and ends on v. It starts on w and ends on v, becomes v minus w. That kind of make weird sense? Yeah. I'll do another
W
one.
minus v goes the other way though.
If I have, it's pointing the same way.
No,
He just said
W,
W minus
W
v.
minus v.
Oh, w minus v would just start at v
Yeah,
and end
it
up
just
at
goes the other way, yeah.
opposite direction. So they're negatives of each other. So if this is r vector, and this is s vector, running out of letters, what would be
You got 27 to use.
s minus r? What would be s vector minus r vector? Where would you start and where would you end?
You flip. If you want to go parallelogram,
I don't want to do parallelogram. I want a shortcut.
oh, air to air.
Where to where?
From S to R.
Nope. That's where people make their mistakes. Here, remember, it's v minus w, and it goes
That's right.
w to,
It would be R to S.
it would be r to s. So it starts at r and goes to s.
You can't talk with it.
Ta-da. so far all I've done is messed around with the pictures. So far all I've done is messed around with the pictures. Now let's deal with vectors in a coordinate system. Because obviously if they have direction and magnitude, I can throw it into a coordinate system, kind of like a watch hand, like radian or polar coordinates. And there's a lot of similarities between this stuff and polar coordinates. So,
Coordinates.
new page. Coordinate planes and vectors. So, in a coordinate plane, a vector can start anywhere and end anywhere. So basically between any 2 points. So if I choose this point to be the start, I'm going to call it P. And this point over here, to call it the end, I'll call it Q. And I want my vector going from P, ending at Q. Now P, of course, has coordinates, x1, y1, and Q has coordinates x2, y2. All right, I can put those in. x1, y1, up here, x2, y2. Okay. Now, to designate this, we can call it vector v, except that has nothing to do with p and q. So another way of designating vector v, so it's a little bit more, this is so squeaky, understandable, is it starts at p and it ends at q. Now, in geometry, you would say PQ and put a little line above it would represent the line segment PQ. If you put a PQ with an arrow on it, it used to be that it was a ray. So be really careful. This is just a vector. I don't put the little arrow on top. I put half an arrow. All right, so this is also known as vector PQ. What if I put the Q first?
It's QP.
And which way would it point?
The other way.
The other way. So it's really important which letter comes first in terms of a vector lost someplace in the coordinate plane. My problem with vectors lost in the coordinate plane is we've already said that we can put them anywhere we want. So where would be the best place to put this thing?
Or the origin?
At the origin. Start it at the origin and let it point in any direction that it wants. So if I start it at the origin and have it going in any direction I want, well, the direction that it's going in, as long as the magnitude is exactly the same, and as long as the angle of inclination is exactly the same, they're the same vector. So, how do I get P to get down here to the origin?
Make it equal to 0?
Yeah, but you can't just make it equal to 0. You've got to move it along the coordinate system.
Well, I was going to say, we don't know exactly where P is.
How far to the right is it?
That's it.
x1. How far up is it? y1. So all I have to do is move it x1 to the left and y1 down. So x1 left,
That's if it wasn't 1 to the.
y1 down. And of course,
Just
yeah,
if
if
it
x
was-
is to the left, then you'd move to the right.
No, you're saying x1 to the left. Well, what if x was 2 and be 2 to the left? So it's whatever.
Whatever x1 is.
Okay. Well, you said 1, and we don't know what it is.
I said
No.
x1.
Because there's an x1
Oh,
and
X
y1.
sub 1.
I thought you meant like x1 to the left.
No. X sub 1 to the left, x y1 to the down, from where I've drawn it. Now, if x1 is negative, you would be moving to the right, and if y1 was negative, you'd be moving up. But I kept everything in the first quadrant, so it's nice. Now, if I move x1 to the left and down y1, how does q move? Remember, I can't change the length, so everything has
It's
to...
the same thing.
So, what would I write for x2?
It's the same one.
How do I make it go down x1? For that one, it's easy. How do I make x2 go down x1?
x2 minus x1.
x2 minus x1. And
Same thing as was.
y2 minus y. So this becomes the coordinate for q that has been transferred so that pq is now starting at the origin and ending at some other coordinate. Okay. So let me draw that picture. So here we're starting at the origin. We're going to call that p prime. Because it's not really p, because p is x1, y1. And then someplace over here you're going to have q prime. And your vector is here. And this coordinate is, of course, x2 minus x1, y2 minus y1. So in vector language, we can consider this, that's just a coordinate. To mean or to demonstrate that this is a vector stopping at this coordinate and starting at the origin, we're going to write it this way. And that becomes our vector. So with these weird braces on the end of it, it's going to be considered vector language. So you put those things on the outside, it's automatically called a vector. Parentheses represent a point. So here you have a point. Here we're going to have a. So let's simplify this into one sentence. Given vector PQ where P is equal to x1, y1, Q is equal to x2, y2. Vector PQ then becomes known as the vector x2 minus x1, y2 minus y1. It's a simple little formula, but guess what people forget? The simple little formulas. I'll give you 2 points on the test and I'll say come up with a vector, and a lot of people are going to forget that all you have to do is subtract the coordinates. But the order is important. It has to be the second coordinate minus the first coordinate, otherwise things are.
It's all about differences.
Yeah, if you turn it around, the vector literally turns around.
Yeah, flip-flops.
So you got to be careful. Now that's called vector components. All right, so vector components. Wake up back there. We write vectors like 2, -3. I told you, it's a lot of little pieces that make up the whole. What did you say? Do I really want to know? No. It's a lot of little pieces, and not one of the pieces is hard. It's just when you have all the pieces together, you have to remember way too much for a while. So you do have to practice this stuff. All right, so if I have the vector v is equal to 2, -3, how would I draw it?
It goes from the origin to -3.
It goes from the origin, so here's your start point. And 2, -3 would be 2 to the right and 3 down. So that would be your end point, and your vector would go like that. Easy. As long as you remember what you're doing. Okay, what's next? Oh, let's talk about simplistic scalar. So if I did 1/2 v, what do you think would happen? Well, I want to take the magnitude and cut it in half. So that would be 1/2 of 2 -3. Is there anything that tells me what to do next? No. So I'm kind of at a stop right now. The other thing I want to do is I want to be able to add and subtract, of course. So if I have v plus w, I want to be able to take 2 components and actually try to add them together, because I know I can add vectors. It's just that the components are kind of not allowing me to do it yet. So there's one more huge piece to this whole puzzle. And it is this. We'll come back to this. We need something else to allow us to add vectors, scalar multiply, and eventually something else. So, we can do this one. Star magnitude. Remember at the beginning, our definition of a scalar, of a vector is direction and magnitude. So let's just talk about magnitude itself. All right, So if vector v is 2, negative 3, and the picture is this, how do I find its magnitude? Magnitude is the length of that vector. So how do I find its magnitude? Oh, we've been doing this so often. Take polar coordinates. How would I find the... I forgot the name of that thing again. Not the argument.
Is there ways to look at y equals cosine?
No. I don't know what the angle is. What should I draw? A triangle. If I draw a right triangle, this side is negative 3, it'll go away. This side is 2, and how do I find the third side, r over here?
It's squared plus squared equals r squared.
Well, c squared equals a squared plus b squared. It's not on a unit circle, so I'd rather not do that. C in this case is r. A in this case is 4. B squared in this case is 9. So you get r is equal to
Square root of 13.
square root of 13. So to designate this, we're going to write the magnitude of v as like two goalposts, like absolute values. Some books will just put the 2 lines, but it looks so much like absolute values that some books put the double line. Is equal to the square root of 13. It's the magnitude of v, not the vector v. Now, big difference. Vector v is obviously a vector. Magnitude of v is what do we call these things? When they're just numbers.
Huh?
What did I call numbers so far in my argument today? Discussion. Just a number. We've been talking about vectors, but there was another thing we've been talking about. Begins with an S. Scalars. Square root of 13 is considered a scalar. So when we start talking about numbers, they're just considered scalars. So in vector language, you don't say number, you say scalar.
So you said that the double
Bars.
is saying that's the magnitude of v,
The magnitude of v.
not magnitude of vector v.
Well, magnitude of vector v, sure. I'm saying it's not a vector
So then why'd you put the vector symbol up there?
because it's the magnitude of the vector v.
But you just said it wasn't a vector.
It's not a vector, it's the magnitude of a vector. What's the magnitude of the vector? It's length.
So
And
that's
length
magnitude
is a
2
distance,
lines,
and
yeah.
distance is a scalar. Those drugs are messing you up, aren't they? Messing you up.
They're getting to your head.
So the formula for the magnitude, we'll start off with this. If I have a vector v is equal to a comma b, then the magnitude of vector v is equal to the square root of a squared plus b squared. This is really important. It'll come back and come back and come back over and over and over again.
Let me copy that.
How to find the magnitude of v. But it's also the same way as finding the radius in polar coordinates. It's also the same as finding the third side of a triangle when we're doing trig. It all turns out to be about the same. And I'm trying to go slow through this because usually I fly. Because they're really not that hard, but then I find people have difficulties with the concept of vector and scalar.
Scalar.
And magnitude and direction, all that mess. Scalar. Okay, now we can talk about this. Also an important topic. Unit vector. What's a unit circle?
One. It's all one out from
What's one?
the
Circles only have two things, a center and a
radius.
Radius.
The radius is 1.
the radius is 1. So when you say unit circle, the radius is 1. When I say unit vector, take a guess
The
what it
magnitude
means.
is 1.
Magnitude is 1. So the mag is equal to 1. In other words, if I take the magnitude of any vector, it's going to equal 1. Now unit vectors are really good because I can take a unit vector and it scales really nice. If I need a vector that is 5 units long, I take a unit vector which is 1 and multiply it by?
What?
Okay, I need a vector that is 5 units
Multiply by
long.
5.
You just multiply by 5. If I want a vector that's 1/10 the size, I just take a unit vector and multiply it by 1/10. So this allows me to,
It's very scalable.
for easy scaling. Very scalable. Yeah, that works too. Very scalable. Allows.
That's what I said.
No,
How
it's
do,
a lose.
how do you spell allows?
You without the E.
Fine.
Allows.
Allows. Whatever.
Are you okay?
I'm not.
What kind of drugs did they give you?
I think he's crying.
Oh, I made him upset.
Yes, because you couldn't spell allows.
Shh, quiet. Delete.
Very Nazi.
Degrees.
Degray.
All right. So how do I find a unit vector?
Ow.
So if I give you v is equal to -3, 5,
On a unit vector?
is that a unit vector? Do you think? Well, find out. The magnitude of v is equal to the square root of
-3
I
squared.
thought it was
-3
just,
squared.
The magnitude of v was just 1.
I'm saying, notice the squiggly line, separate ideas. If you have a unit vector, the magnitude of the vector is going to equal 1. Yeah, just go to sleep. You watch the video later. So the first one's going to be -3 squared, which is 9. 5 squared, which is 25. So the magnitude of this vector is the square root of
You just remembered that.
34?
Did I give
34.
you anything that had still in it?
No.
So is the magnitude of this vector 1?
No.
No. Can I make it 1?
Yeah.
Yes.
Maybe.
This is the trick. We're going to take v, and we're going to divide by its magnitude.
Now it hurts.
That's really bad.
So take your vector v
Should we gotta hook up your mom and get those extra drills or something?
and divide by the square root of 34.
Just like, mom.
Shoot him out the game and play the first time.
I feel great.
Okay, I'm stuck again for a little while because I've already said we don't have anything that allows us to multiply vector and scale.
Yeah.
Even though I know we should be able to, I don't have a way of doing it with components. So we'll come back to that in a second. But I needed that idea of a unit vector for one thing. And then it all comes together rather nicely. So it's all separate pieces. I got to bring it together. We need to get away from components and talk about vectors a little bit different. If I have a coordinate axis, and I choose a vector to point in this direction, and the magnitude of that vector is 1, then we're going to call this vector I hat. The hat actually represents unit. So it's a unit vector in the I direction.
I was imaginary.
In vector language, it's something else. So don't get it confused with I as imaginary.
This is all math language.
But notice the little hat. It's wearing a hat. It's different than just
It's
an eye.
wearing a hat.
It's a fancy eye. He's got a hat on. All right. If I choose,
It's aristocrated eye.
it's aristocrat eye. If I choose a vector to go straight up the y-axis 1 unit, make that a fancy one. This is called
Isn't the same thing?
j-hat. I makes it go to the right. J makes it go up. Okay. So if I take, I'm going to just draw a big ugly picture here. And I extend it 5 units. So this would be 5i.
Why 5?
Just 5, just for fun. I'm making up a problem. If I move it 5i to the right, and I use j, and I use j as 3j, this would be 3j. Don't forget the hats though, because otherwise I by itself is just an imaginary number. Can I add these two vectors together? In other words, can I find 5i plus 3j? How would I do it?
Picture.
Draw a, what kind of picture? How do you add two vectors together?
Parallel one.
Parallelogram. In this case, what kind of parallelogram are you going to get? What kind of parallelogram? It's a special one.
Really?
Yes. The one that you always draw.
What kind of angle is this?
Already.
It's a 45. Oh, it's a 45 degree.
And if I draw a parallelogram with a right angle in it, what does it become?
Square.
Well, close, no cigar.
Rectangle.
Rectangle. So I get a rectangle out of this mess.
No way.
And you get that.
Ryan just
Take him home.
he drove himself. That's the problem.
He
Huh?
drove himself?
Are you serious?
This time he did.
No, you said parallelogram, they're like rectangle, and he's like, no cigar. What? What do you mean?
Cigar?
I swear I thought you said cigar. I was like, what?
What do you say? No cigar?
said a
Close but no
square.
cigar?
Close with no cigar.
Close but you don't have it. Delete! Delete everything.
I can bring a horse to water, but I cannot make him drink.
Drink.
Eat here, horse. Horse? What does that have to do with this? So,
Ow.
wow. This video is going to be interesting for people in the future to watch. Yeah, we used to let his students do drugs.
I'm telling you, you need a blooper reel.
So, this is it. If I want 5i plus 3j, that would be this vector here.
He is giving me life right now.
Alright, shh. Calm. So, 5i plus 3j would be the vector that's the diagonal of this rectangle. What's the coordinate of this point if we were just talking about regular rectangular coordinates?
It's 5-3.
It's 5-3.
J something.
Well, no, it's 5i plus 3j is this vector, but the coordinate is 5-3. But the vector starts at the origin and ends at 5-3. So 5i plus 3j is the same thing as my vector 5-3. So this allows me just to have another notation that splits it into the components into a sum of algebra, it's an algebraic expression, and now I can start proving everything else I wanted to prove.
So that's it?
That's it. I is a vector that goes to the right, j is a vector that goes one unit up, and with an I and a j you can write any vector because they're exactly the same as the components. So 5i plus 3j is the same thing as the component vector 5-3. Starts at the origin and ends at 5-3. Now I need that so that I can prove addition, prove scalar multiplication. Those are the two main ones. So let's go back to scalar multiplication. Scalar multiply. Let's have a vector equal AB. And let's find out what k times that vector is. So before, all k does is it will extend the vector v further forward, make it a little bit shorter, or actually make it go backwards. So on the other side, that also becomes k dot ab. And I said earlier, I don't have anything that says what I can do from that point on. Go ahead.
You didn't put an arrow on top of the V.
Ah, where? Oh,
yep.
I did. Wow, that's unusual. So what I have to do is use my ij notation.
Wait, is K supposed to have a line?
K is a
Oh.
scalar, a number. So k is a scalar, v is a vector. So here I have a scalar times a vector. But I said already that I can't work with this, so I'm going to convert it into ij notation. So this becomes k times, parentheses, ai hat plus bj hat. Now, it goes from the weird endings, the vector notation, into parentheses because this is just an algebraic expression. All right, now can I deal with the k in an algebraic expression? Sure, how?
Just multiply.
What's that? How?
Distribute.
Distribute. So this will give us ka I hat plus kbj hat. Now put it back into component language. What would be the first place? Where A went to a I hat and B went to bj hat, what goes in the first position here?
K.
K.
A.
K. There's no I up here. with A.
K-A,
Ka. And down here?
K-B.
KB.
So
what really happened
the
was
shortcut was just
to distribute. But I couldn't say it mathematically because it makes no sense. Because then I'll see you guys doing this. Oh, 3 times the coordinate 2, 4 is equal to 6, 12. And that makes no sense to multiply a coordinate by a value. You see what I'm doing? It turns out to be the same thing, but this doesn't make any sense. Here, this makes absolutely no sense because this is a point.
Ryan, some shortcuts.
And there's no way of multiplying a point by a number. But if it's a vector, it allows you. So this is k times vector e. You can't just do things in math and go, yeah, it works.
It makes sense to me though.
Well, it makes sense, yeah, but in math, you have to prove it actually works. And then you can use it.
Well, now I know that it does work.
Now you can use it.
I was going to use it to begin with.
Fine, just use it now.
About to roll out.
Sum, or addition, subtraction.
Personally, I say,
My babysitter got a job.
oh damn.
That's, the other thing is I'll ask you to prove one of these on the test.
Should I say, are you good?
No, you try saying.
Yeah, really.
Ouch.
He's young and
I was trying to say,
so here, I want to find v plus w, which is going to turn into AB component plus CD component. Now, again, can't add them because I have nothing to do with, there's no way of adding a point to a point, because that's kind of what we're looking at. So I got to change it into IJ notation. So this becomes equal to, what's AB in IJ notation? AI plus BJ plus CI plus DJ. Now what?
You have like terms.
You add like terms. So the like terms are I. How do I add them?
ACI squared?
That's multiplying
Oh yeah, that's right.
them. And you can't have I squared, it makes no sense to square a vector. There's no math behind that one. I'm going to take this magnitude and direction and square it.
You get negative 1 hat.
No, you don't get negative 1 half.
Oh.
So, what is AI plus CI? AI plus CI?
It's a half, let's see, a half.
Yeah, but what does it become? If you have 2x plus 3x, they're like terms. How do you add them together?
It's 5x.
Yeah, but how?
The 2, so the A and C.
So what do I do with the A and the C?
Put them together, AC.
Oh, so it's I hat multiplied by A plus C.
A plus C.
What?
So it becomes A plus C, I hat.
Oh.
Because up here it would be 2 plus 3,
X.
x.
Okay.
Okay. That's actually the distributive property backwards.
Yeah.
Next one is,
I'm smart. Yeah.
Okay.
what's left behind?
B and D.
Well, be precise.
B plus C.
There's no B over here. Oh, I'm sorry. We're looking at the J's. This one?
Jesus.
I was looking at the C and the D.
Jesus, man.
So it would be B,
B, that's a B and D.
yeah, B and D, which and is actually multiplication, by the way. Plus.
You said what was left. I said B and D was left.
I know, B plus D is left. Oh, you're so
sit over there.
I wasn't standing.
So this becomes in component language, a plus c, comma, b plus c.
Just chill there, Ryan. Just chill. You'll be fine.
So, adding vectors together, you add their first components and then their second components.
I was
That's where
gonna
they
say
change the
that.
time again.
It is now back to 10:45.
Yeah, something, some junk, you know, they get those garbage ones. Okay, so let's put it into an example. V equals 2, -3.
Dang.
W equals 4, 7. What is -1/3 of V?
I don't like this.
What is
Whoa.
-1/3 of V?
Oh, of V?
Of V,
Well, you
That would
just
be
multiply- you just
negative 1/3
multiply,
multiplied by 2,
which is
a number.
2 divided by 3.
-2/3, better known as,
Negative 2/3.
comma,
1.
1.
Yeah, and then 1.
-3 times -1/3 is 1.
Is it really 1?
Did you actually get your calculator out? Oh, that's sad. The 3's are going to cancel.
I
Negative
guess
times a
you got it
negative
right.
is
I'm on
a
drugs.
positive.
Yeah, shut up.
Ah. How about 2W?
Now I gotta worry about how you're gonna get
2W.
Kira can walk down now.
Okay.
2W.
It's 2 times 4.
Which is
8/21.
comma.
So he's about to slap his other face.
I'm about to, yeah. I bet it'll hurt him too.
It depends on which side.
How
it
this?
is.
I'll hit the right hand side, so it shocks the left hand side into no pain at all.
No, this is no longer numb. That's
That's what I'm
feeling
saying. I'll
pain.
hit this side, and you won't feel that side anymore.
What?
The other side will hurt worse.
I was about to say.
No.
What about V plus W?
Ryan, you're still on drugs.
V plus W.
It's gonna be 6 and 4.
6 and 4. Because you add the first two, and you add the second two. Not hard, right?
But you have to prove it.
I proved it, now we can use it. That's the beauty of it.
I was trying to use it without proving it.
Prove it and
Yeah,
use
but
it.
then you get into traps where what you're using really isn't even provable.
Watch him
Prove it
like
or
what if he like
use it.
never taught us this stuff on the test? I just did that. He's like, how'd you do this? You didn't prove it. Be like,
So here's the direction we're going to give it. Salt and sugar. Ew. Theta. How do I find the magnitude?
make a triangle.
Let's call this vector v. V equals
So you made a rectangle.
AB. Make a triangle.
Triangle, whatever. It's always triangle.
How far is it from here to here? You know, along the side of the vector.
We'll know once we find the other two sides.
Yeah, but how do you find it?
They're the lengths.
Without even finding the other two sides.
Tangent.
How do you find the magnitude of a vector?
Sine, cosine.
There's a formula on your piece of paper that you should have written down.
John. We got this. Just give us
It's this what?
a second.
It's the
Is that
X2. Oh.
oh,
No,
it starts with that.
Oh no, I got it. Yeah. Square root of a squared plus b squared.
so this side is the square root of a squared plus b squared.
I want to write that down.
Fine. This side then, of course, is A, and this side is B. I want to get angle theta involved.
Tangent. No cosine.
Well, you could do tangent B over A and come up with an angle, but I wanted to get involved in the I direction and in the
So sine and cosine.
sine and cosine. So if I set up sine of theta, what's it equal to?
B over that.
B over the magnitude of the vector. And I'm just going to leave it as the magnitude of the vector, rather than square root of a squared plus b squared. Now, what you can do is you can solve for b. What's b become? If you solve for b.
It's sine theta over.
It's not over. How do you solve for b?
What?
How do I get b by itself?
No, you multiply.
By?
B?
Oh, you
By the magnitude.
by the magnitude thing. So it becomes the magnitude of v sine theta.
Yeah.
Okay. If I want to find a, I would write cosine of a is equal, theta. God, I'm messing
The
up.
vector cosine theta.
Is equal
That'll
to
be the magnitude cos.
a over,
A over
magnitude of
vector. A over the yeah.
and therefore a is equal to?
The magnitude cosine of theta.
Magnitude cosine of theta. Okay. That should look really familiar. What's it look like?
I don't know.
Something we went over before.
Something we went over before.
Did we just go over it Monday or Friday?
Monday, yeah. What was it? What did we teach on Monday? No one
Two
remembers.
things. Two things.
Two things, but it was the first one.
I have one.
Say it again.
I have this.
Polar coordinates. That's the same formula. He's like, I wanted to find
I
it.
just had it.
This is the same formula that x equals r sine theta, x equals r cosine theta, y equals r sine theta. It's the exact same setup for the same reason, actually.
Why?
It's just they're talking about the same picture. I mean, when we did polar coordinates, it was this picture.
Yeah.
And now we call it a vector, and it just turns into the same picture. All right, so
Everything in pre-calculus triangles.
if I convert
Told you.
AB into AI hat plus BJ hat, then this vector is going to become, A is magnitude of V sine theta, so this would be magnitude of V sine theta I hat, plus, and B becomes magnitude of V sine theta, magnitude of V sine theta, J hat. Now out of all that mess, what's the only thing, oh, wait, one of them's wrong. Which one's wrong?
The sine.
They-
You have to
they
have
both-
cosine.
They both say
Which
sine.
one is cosine?
J. No.
It's
No,
I.
What?
It's I. So this should be
Okay,
cosine
fine.
of theta. Cosine always goes with the x coordinate. It's the first
Right.
one. It'll always be the first one.
Think of it always as it's.
All right. Now, other than the signs being exactly the same, is there anything else in common?
The magnitude.
The magnitude. So I can factor out the magnitude. What's left behind is cosine of theta I plus sine of theta j. And I usually don't like i's and j's. I like i's and j's because it allows you to do the algebra. But after you get them, I like going back to components. So this is the magnitude of v times the vector cosine theta sine theta. So a comma b can be written in terms of its magnitude and its direction theta. So this is mag, and the theta up here is the direction. And that's the pure form of what a vector is. It shows you the magnitude, it shows you the direction.
I'm not
Hmm?
gonna do
Then write it down.
That would be
that.
helpful.
Well, now that I haven't written out any of it, if he's erasing it, there's no.
I'm only going to erase up to here.
You just erase what I was gonna write down.
All that? You said all, the only important thing is the last thing.
So 11 B lines off 11 cosine.
11?
The two lines is 11.
Fine. Don't read it as 11 when you're thinking scalars, though. All right, for example, plane is flying north 15 degrees east at 250 miles per hour. Find the vector that goes to this idea of this flight. Now, it doesn't say how long it's flying. It doesn't say anything else. It's just direction and magnitude.
So it's 75 degrees from the right.
So if this is north by east, this is 15 degrees,
Yeah, and there's 75 degrees.
and this would be
there.
75 degrees. So theta is 75 degrees. What's the magnitude?
150.
100.
No, wait. 250.
250. So this becomes the magnitude of the vector.
Wait. What? Yeah, magnitude would be velocity.
Yeah. Velocity, weight.
I was like,
Something that-
how long? Because if
It's 250 long.
Yeah.
You're not flying that distance. It's just that's the magnitude of the vector.
Yeah.
How fast you're going. All right, so when I want to write this vector v, it starts off with magnitude of v time, component, cosine of theta, sine of theta. Oh, just a little refresher. If this was a coordinate, cosine theta, sine theta, where would it be located? If this was the coordinate, cosine theta, comma, sine theta, where would it be located?
At the tip
On what picture?
of that picture.
On what picture? Just any theta.
Before that,
Any theta.
unit circle.
Unit circle. This is the coordinate of a unit circle times magnitude. So this is literally, I'm pointing in a certain direction, and I have this specific magnitude.
So it would be 1.
Well, the magnitude of that vector is 1 for sure. Sine theta, cosine theta. This vector here is magnitude of 1. This changes it because it's a scalar on top of that.
So whatever the magnitude is, just multiply by 1.
That's how long it's going to be. It keeps it 240 in this case, 250. So this vector becomes v equals 250. Then the component is going to be cosine of 75 degrees, comma, sine of 75 degrees.
So how fast it was going is the magnitude.
How fast it's going is a magnitude. How much it weighs is a magnitude. How much force you're applying to something is a magnitude. Now the direction you apply the force or speed or weight varies depending on the situation. Okay, last step, calculator time. You're going to distribute. So 250 times cosine of 75. Then I can write my vector perfectly. 250 times cosine of 75.
64.7.
What is it?
64.7.
64.7, comma, and then 250 times sine of 75.
241.4. 5.5.
0.5.
0.5. 148.
0.5. And that would be the specific location of the end of that vector. So if you could actually plot this on a piece of graph paper, you would know a couple things. The angle between your vector and the vertical line is 15 degrees, and the other angle has to be guaranteed 75 degrees. And the length of that line vector is going to be 250. Now we can do some fun stuff if I have time. I got some time. There's time. At this point, I have a huge rock, whatever, slab of thing you're going to move. And the way we're going to move it is by attaching 2 ropes to it. And on this rope, people are pulling with 400 pounds of force. And the angle here is 25 degrees. There's another group of people pulling in this direction with a greater force of 500 pounds. And the angle here is
10.
10 degrees, sure, that would be fine. Now the one angle to be really careful about is that 10 degrees. Why? It's negative 10. It's going down. So when we do our calculations, it would be really important to make that negative 10 in our cosine and sine. So what I want to do is, what direction and total magnitude force is this slab being moved? So I need to find the magnitude of the combined forces and what direction the combined forces is actually moving in. All right. The slab. So how many vectors do I have here?
2 vectors.
2 vectors. Give them special names. Call this one vector V. Call this one vector W. Okay. So what can I say about vector V? Is there a way of finding it? Yeah, same way we did over there. What's the magnitude?
400.
400 times the vector cosine of theta sine of theta. Well, what's theta in this case?
25 degrees.
25 degrees. And then just multiply it out. 400 times cosine of 25?
362.5.
362.5, comma, 400 times sine of 25.
169.
Oh, I was going to say 0.0. Seriously?
Yeah.
Is that close? That's pretty cool. All right, what about vector W then?
You do the same thing, but instead of 400, it's 500, and instead of 25, it's negative 10.
So cosine of negative 10 and
492.4.
sine of negative 10.
There's a fire burning.
Get out of my way.
The same.
What's the first one?
Huh?
First one.
Oh crap! It was like 490 something.
I want to be precise.
Yeah, I know.
491, I think.
No, it's 492.
490?
492.4.
Yeah.
492.4. The next one? Should be really small.
21.
Negative 86.82.
86.82 and 8. Nearest tenth should be fine.
Then you add them together.
Then I add them together. So how do I add vectors together?
First one, second, second.
We'll literally add them exactly the way they're lined up, which is nice. So V plus W is equal to the sum of the first two, which is 850.
854.9.
854.9. The next two, I'm not going to do that one in my head.
Hold up.
169 minus 86.8.
82.2.
82.2.
82.2.
I had it right.
Yeah,
Now-
82.2.
This gives you an idea that this thing is moving in the first quadrant. So even though the force coming down is bigger than the force going up,
Your angle.
the angle's bigger up here and it's actually moving
That way.
in that direction.
Yep.
All right, now the next part is, what's the magnitude? So if I have to find the magnitude of V plus W, how do I find it?
That's the square root of A plus B.
Yeah, it's the square root of the first number squared plus the second number squared. So I'd rather you just type it all in one fell swoop. Second square root, 854.9 all squared plus 82.2 all squared, hit enter.
$858.8.
858.8, and this would be pounds of force.
Yep.
So this thing is moving with a combined total of forces. Now, if I just added up the forces, 500 plus 400 is,
Can't do that.
900
It's
pounds.
Can't do it.
and it would work fine if they were
Straight
being
in.
pulled in the same direction. But because you're separating the forces, you're actually going a little bit less than 900. All right, how do I find direction?
Didn't we just do that?
The direction for the first force was 25 degrees. The direction for the second one was -10. What's the direction of 854.9, 82.2?
Oh, so you want the theta, right?
I want theta.
Oh.
How do I find theta?
Cosine inverse? The
I
inverse?
could do cosine inverse, but
Cosine
then
inverse of the first, sine
I'd
inverse
have
of
to
the
use
second.
this number over here. What's an easier function? Using just these two numbers.
Maybe tangent.
Tangent, just like with polar coordinates, tan inverse. So theta
It's gonna be
is equal to tan inverse of what?
isn't it 82?
82.2 over 854.9.
Ouch.
What's that equal to? It should be relatively small. I'd say less than 10 degrees. 1/10.
4?
You're guessing 4?
The answer is not always 4, Ryan.
He's feeling a little bit better, I think.
5.5, 5.49.
5.49.
It was close. And I had a 4 right in there.
5.5 degrees. Now, if I want to put it in the language of north, west, east, that type thing, do you remember how to do that?
It's,
Is he going
This would be north,
it'd be north, hold on, north 85, no, 84.5.
84.5
East.
degrees east. Just in case you were having fun.
Yay. I just didn't remember, I just looked at the example.
There's one more thing we can do with this, but we actually have no time. So we'll cover this on Friday.
Yeah.
And I have a lot of fun.